Obrigada for this kind invitation. Okay, I have to say that I am very impressed that with so many people. I'm also very impressed at all the organizers, which are Anna, Daniel, Fernando, Marcelo, Tiago. They were all, aside from Marcelo, which is one of the organizers, they were all students like you in these lectures. Okay? And even Christian, that is going to talk after me, the speaker, also was a student of this school, which makes that very nice, and of course tells you that you will be in a few years organizing the school, being professors. This is very nice. So the lectures, I say that, okay, I'm going to talk about entanglement, but also Ottfried Bühne is going to talk about entanglement. We are sharing different things, so I'm going to do mostly bipartite and finite systems. And then there is also Eugene Potsik that has not yet arrived, but he will also talk in a different context. So, well, I am in the University Autónoma of Barcelona, ICREA professor. I am in Women for Quantum, an association that we are bringing, and I think it's a good moment to always claim for peace, and this is the reason that I feel that I have to say that it's a very important thing to change the world, because how it is going is not very nice. So, why entanglement? So before proceeding, Ottfried and myself will say that maybe it would be nice if somebody of you would like to latte our talks or transferences to have some notes, because they have to be in this format, but well, Latin things are very easy, as we all know. There is these machines that put it there. But if there is somebody who likes to take notes and so on, and then wants to talk with us, we thought that maybe we can do something together and maybe put it in the archives. Okay, as the notes of Quantum Paraty School, which will be nice. Okay. So, well, why entanglement? Okay, so I'm going to talk about entanglement first of all, because entanglement is at the heart of quantum physics. I'm not so much in quantum technologies, but this is physics, okay? And this is very important. And also because quantum information looks for information processing tasks that might offer some advantages. And indeed, understanding this kind of tasks, it's fundamental and forms the foundation of what will be after quantum technological applications. And entanglement is necessary, and it's in the heart of many of these applications that we know. So this is why entanglement is important. So how I have organized the lectures, so I imagine that you come from very different places and the level is very non-homogeneous. So my task in this first lecture is to put a kind of homogeneous level that we feel all comfortable. So some of you will find it very basic. There is not always trivial physics, so it's okay if you know it everything and listen another time. So what I was thinking is that I will, first of all, we will warm up today, that many of you just have arrived, so you are a little bit jet lagged maybe, with remembering a little bit the postulates that we will be using and the notation. And then I will go to define entanglement in the case of bipartite, pure states, and as I say, Ottfried will talk about multipartite. Then I would like to look at some non-trivial protocols that they show why this entanglement is really at the heart of quantum physics, and it's also interesting because it allows us to do things that classically we cannot do. And then I will introduce the problem of separability entanglement for mixed state, which is what we call an NP-hard problem, so a priori a problem that doesn't have a solution, but we know a lot of things since we started. I have to say that I have been working in entanglement for many years, and Ottfried was a PhD student of us, which is also a professor working on entanglement, so it's a very vicious subject. If you start to work in entanglement, it's very difficult that you don't work in entanglement for many years, so be careful about that. And then in the last lectures, I want to do certification of entanglement, so we would like to know how can I know if a state is entangled or not. This is why it's so difficult and it's really hard. And there are many things, partial transpositions, materializations, entanglement, and quantum maps. And I would like to do, the level will be a little bit more high in quantum maps. And then I want to quantify entanglement, and we see whatever we reach. And again, this is complementary to the lectures of Ottfried and Eugene. Okay? So today I want to see how far I go, so I have prepared something like that, which is these postulates, and then I will talk mostly about composite systems. I will show what is entanglement in pure states. I want to show some protocol that uses entanglement in these pure states. I want to talk about mixed states, and if I have time and we reach, it depends how we go, we will go to entanglement in mixed states. So warming up. Okay, so I know that you all know that, but I don't mind, because I like to start from the beginning. Okay, and I'm going to talk only about the postulates that I am interested on. So I don't need the 6 or 7 postulates. So of course I want to talk about the Paraty postulate, okay, because this is how we are going to talk about if we have an isolate pure state, and this is important that it has an isolate pure state. Okay, there is always associated a Hilbert space, and then the system is completely described by a state vector psi, which is a unit vector in this Hilbert space. And then we have the second postulate, which tells us that if the state is closed, which means exactly the same as being isolated, it doesn't interact on anything, we know that quantum mechanics has to be unitary evolution, and there is no time reversal, so it has to have direction unitary or anti-unitary. Okay? And that will have some importance when we will look at entanglement. Okay? So, and we normally write it like that. So the state of my isolate quantum system after a time, okay, whatever it has happened has to be described by a unitary operation over my initial state. It's here, okay, this is a unitary operation. And then we have this postulate, which is fundamental for us, quantum information, because at the end, quantum information is nothing else than describing a system, see how this system evolves, and measuring the system. Okay, so this is how we do it. So, and we know that measurements are described by operators. So I would like to tell you that vectors are vectors. So an operator has to have a matrix, because transforms here, vectors into vectors. So the only animal that transforms vectors into vectors are matrices. Okay, so quantum physics is done in several formalisms, but we use this algebraic method to work. Okay, and these measurements, they have to, because the probability that you get an outcome, so you have a measurement m, which gives you an outcome small m, okay? And the probability that that happens when I measure my system, it has to give some outcomes, so it has to be 1 with probability, and this is this condition. So if I have a collection of operators, of matrices, that fulfill that, this is a valid measurement. So, and then we know, all right, so this is the typical postulate that the probability of observing this outcome is given by this expression up here. So m apply over psi, and this transform my state, so this has to be a probability. I have to multiply by the complex conjugate, which is that, and the post measurement is this one. Okay, so typical example, I want to measure a qubit. Okay, so I need 2 operators, for instance, 0, 0, and 1, 1. These are 2 matrices, 2 by 2. This one is 1, 0, 0, 0, and the other one, they are diagonal 0, 0, 0, 1. But I want to say that because I want to give you the feeling that this is really all that we need to have. Okay, we have to be able to deal with matrices and with vectors. And here we go, our postulate. Okay, and this is the 4. I put it the 4, I don't know which is, but because it's the only one that I'm going to spend a lot of time. It's that the state space of a composite physical system, it's given by the tensor product, okay, and this is super important, of the state spaces of each of the constituent parts. So if I have n different systems, and I want to describe this system, I will describe it with this tensorial product. And the way to write it compactly is to put a big cross dot of these different Hilbert spaces. And why is that? So we learn that and we say, yeah, it's like that, okay? But why? Because I have a composite system, so I have the system A and the system B. why I cannot give that the result of that is A plus B? Why this is not correct? Okay? This think of it's not correct. I can never describe my system like A plus B. I have to describe it as a tensorial product. So imagine that I have two systems. System A, it's just a spin, one half, up, and system B is a spin down. And I want to describe A plus B, and I will write that my state is in 0, 1. But I will never say that it's in 0 plus 1. And the reason is that if I was doing that, I will not be able to keep the properties of the Hilbert space. So it will not be, for instance, a principle of superposition. Because if I have two identical spins, how can I distinguish that from a superposition from 0 and 1? Okay, so the fact that we have a tensor product, it's not only because in the books appear, it's because it means something, and this is what I would like to stress. Okay, it has to be like that. Okay, so since we are going to talk about composite systems, let me talk a little bit about which are the properties of these composite systems. So from a mathematical point of view, the first thing that we have to do is to define how is going to be the product, okay, the tensorial product of two Hilbert spaces. So I'm going to talk always about finite systems, okay, finite dimension systems. And in a finite dimension system, a Hilbert space is exactly the same as a complex vector space. If the system is not finite, it's not the same, and that this is the reason that it's called Hilbert. Okay? But if it's finite, it's equivalent. So the first thing that I would like to do is to define the basis. So imagine that I have two Hilbert spaces that I will call it like H1 and H2. There are two vector spaces complex of dimension D1 and D2, respectively. Suppose now that I have a basis which is orthonormal in H1 and another basis which is orthonormal in H2, then an orthonormal basis of the whole Hilbert space is the tensorial product of these two bases. How do we do it? Okay? Once. Okay. So let me give you some properties of this tensor product. First of all, if I have a Hilbert space which is the tensor product of n Hilbert space, the dimension of my Hilbert space is the product of the dimensions of each Hilbert space. Sounds quite logical. So if I have two qubits, so many things. If I have qubits up, okay, it can be up, down, up, and down. Logically, I need 4 elements on the basis to describe that, 2 times 2. Then, as I say, whenever the dimension of the Hilbert space is finite, Eugene will be talking, and also probably Christian, about systems which doesn't have finite dimensions, but I don't know, he will be talking. No, he's not talking. But Eugene, yes, I know. Infinite dimensions, because you have continuous variables, position of a particle, okay, so you cannot put it discrete or many other things. Then you will have to have infinite Hilbert spaces and other words. But whenever it's finite, okay, it will be the same as to have a vector, complex vector space. That will be happening. Now we have to say how we will express that. Okay, so now if I have a vector in my Hilbert space AB, which normally comes from Alice and Bob, which is of this form, phi of A and chi of B, where I have expressed every vector as a linear combination of the elements of the basis. Okay, these are complex coefficients, and be real complex, positive, negative, and this is linear combination, and these are the bases. Then I have to do the tensorial product. And the tensorial product is very simple. Okay, I just multiply the elements and I do the tensorial product of the elements of the basis. Equivalently, this is the same. Okay, I will have that this vector, okay, has two B1, B2 components, which will correspond first component of my vector on Alice multiplied by all the components of Bob. Second component of Alice, all of the Bob, So in total, I will have my vector, which lives in a Hilbert space of dimension D1, D2. Okay, so now what happens with the operators? Because I say that, of course, we not only work with the systems, okay, but we want to manipulate a system. And any transformation of a system is given by an operator. So it's the same. So if I have my operator Bob, B, which acts in the first Hilbert space, so transform these vectors, which are in this Hilbert, or these elements of the system, into itself, and I have another operator C, which transforms H2 to H2. It's just a map. Then I can construct an operator which is A tensorial B, okay, which transforms from H to H. And I have to do exactly the same. I write B, I write tensorial C, I write it on this board. Explicitly, okay, the tensorial product of matrices works like that. I take each element of B and I multiply it by the whole matrix of C. Each element, the last element, and so on. So which is the size of this matrix? This is a matrix that has dimensions D1, D2 times D1, D2. It's a huge matrix. And transforms elements that they have, vectors that they have D1, D2. So what else? There is other properties. Okay, so if I have my Hamiltonian, which is a tensorial product, and now I have a unitary transformation, because this is what we are saying, if the system is isolated, it's a unitary, we will distinguish now. We will say, well, I have a unitary, which goes from the big Hilbert space, and we will say that it's local if, and only if, I can write my unitary as a tensorial product of matrices, each of them unitary. If there is only one which is not like that, that means the transformation is not unitary. It's not a local unitary, it's a non-local. Okay? So, and the same with the measurements. And this is very important because we can decide that we can measure locally, which is much easier, okay, or non-locally. But it will be a measurement that it's local, so if you go to a lab and I have my spin 1 and my other spin, maybe I will be able to measure this spin on one side and this spin, and that will be a local measurement. But of course there are measurements which are very interesting, which are not local, that they don't correspond that Alice measures something and Bob measures something, but rather that we have a measurement in which we measure at the same time the state of Alice and Bob. This is very difficult to do in the lab, but possible, and of course we will see the importance that it has. So, let's recall the properties that we see. So if we have a tensor product, postulate 4, we have that the dimension, it's the product of the dimensions, that we know how to do the tensorial product of vectors, okay, which is exactly, oops, like that. Okay, and then we know how to do the tensorial product of operators, okay, it's tensorial product of matrices. We know how to do it, it's multiplying each element by the matrix of the other. And what is important, why I'm doing all these things, is to say that the tensor product space, written in this way, inherits all the properties of the Hilbert space. Linearity, positivity, if it's necessary, superposition, multiplication, everything. Okay? And that will never happen if we were adding Hilbert spaces, okay, in this way. So this is the reason why the postulate of the composite systems has to be done with this tensorial product. Okay, so now, what are these tensorial products now? Okay, so we have seen mathematical what it means. Now let's see what physically it means. So a priori we think, I'm talking always, I have two spin 1 half. Alice has one, Bob has another one, and I do the tensorial product. But this is not necessarily like that. For instance, I can have a tensorial product if I'm talking about a single particle but different properties. Okay, so for instance, I don't know, position and angular momentum. Why? Because they live in a different Hilbert space. No, I don't know, I want to describe an atom, which I will assume that it has some velocity and so on, and on top of that, on this atom, I will assume that it will have spin, and normally when you say the spin of an atom, it's the spin that is remaining of the electron. Okay, so these are two different degrees of freedom, so I can describe, okay, if I want to describe these two degrees of freedom, I need to have a tensorial product. Okay? But sometimes this is a little bit misleading because position and momentum. Okay, well, position and momentum, no. Okay, because these are not two different degrees of freedom. Okay, position and momentum, they are related, and this is a little bit more complicated. And you can be complicated thinking these things. Okay, so a very prudent way to say it's, okay, let's talk about tensorial product whenever we talk about distinct properties. This can be different particles or distinct properties of a single particle. Okay? What else? And then we will see, okay, well, we will always write it like that because it's very tiring writing all these things, so we always write this means a tensorial product between this system A and system B. And then we arrive already to the first definition, and we say that a composite quantum system is said to be in a product state if and only if the state of the system can be written as a tensorial product of the states of each of the separate systems. And this is very important, okay? Because this is the definition of what it will be an entangled state. So this is so important that I just put the transparency for here. So any state which is not a product state, it's an entangled state. And this also has a little bit of meaning. Okay? Because imagine, I cannot describe an entangled state of what it is. I can only describe an entangled state of what it is not. Okay, so this is very strange, no? Because we deal with entangled states and I say, okay, this is an apple, and whatever it's not an apple, okay? But what it is, I don't know, but it's not an apple. Okay, this is what we are doing after many years, okay? Why? Because we don't know, okay? So we only know how to do it like that. So anything that I cannot write it as a product state, we will say it's an entangled state. Okay, so for instance, typical example, all right? I give you something like that and I say, okay, I ask you, it's this entangled or it's this a product state? So this, I say, this is, tell you this is, I have two Hilbert spaces of the same dimension, 2 qubits, okay? And I have written this state which belongs to the tensorial product, and I ask you, can you write it as a product form? So you see these things of here, and of course, well, I know it because I have done it thousands of times, but I already see that, of course, this system, that it looks like it's not a product state, it is, because I can write that Alice is in 0 plus 1, and Bob is in the superposition of 0 plus 1. And when I do the tensorial product, this is 0, 0, 0, 1, 1, 0, 1, 1. Okay? On here, it looks, it's the same. Yes, it's the same, because I can put Alice is in 0, and Bob is in 1/3 of 0, superposition plus 2/3 of 1. It's a product state. The same will happen here. Okay? This is a little bit more tricky, but we can look like that. But if we try to do the same in the last case, if I try to say, okay, can you please look if there is two product states such that the product of them gives me this state of here, the reason it is impossible. Okay, we cannot do it because it's entangled. Okay, since I cannot write it like something in Alice times something on B, this state is entangled. But of course, it looks very easy, but I can give you instead of 2 qubits, if I try to tell you the same, or I give you an example in which I have many qubits and in a higher dimension, and I just give you the expression, you will not be able to find it. It's very difficult to see if it's a product state or not. Therefore, we have to do it a little bit different. Okay? So, what is entanglement? Well, we can say entanglement is a quantum correlation, which is generic form of quantum correlation, which is due to the tensorial product of the state. There are other correlations, other quantum correlations, non-locality. Maybe I will talk, I don't know if, will you talk about non-locality? No. A little bit, maybe I also will talk a little bit. It's a different thing, okay? There is discord, there are not so many things, to say the truth, but there are other correlations. But entanglement is related to this tensorial structure, okay? Because by definition, if I can write it like a product state with this tensorial product state, it's separable, and if it's not, it's untangled. Okay? Now from on certain very cases, I will only talk, and of course this can be 10 particles that they are entangled on. So it's not related to bipartite or multipartite, but the techniques to show bipartite and multipartite are very different, and that's the reason, and the states are very different. That's the reason that I'm going to talk mostly in bipartite, and Ottfried is going to talk in multipartite. And we will see that the way to generate or to determine if a state is entangled or which measurements or the properties of the states are very different in one case and the other. Okay? It's probably, or for me definitely, it's the most fundamental property of quantum physics. Okay? Because allows to perform things which otherwise are impossible. So, in quantum physics, at least for me, there are 4 things which are fundamental. One is the superposition principle, the other one is the collapse of the wave function, if you want. The other one is that you measure and you can change the state, and the other one is entanglement. Okay? And I consider that this is on the top one. Okay? And of course, you can understand quantum information theory as a resource, okay? Which is capitalistic way to see quantum information, but it's very useful. So you want to do something, so here in our world you want to do something, you need money, and this is your resource, okay? You pay, you get it. Okay, so in quantum information also it's like that. You want to do something, do you have entanglement or not? Yes, you can do it, okay? So then you have to define, this is your resource, this is your money, okay? And you have to define the things which is not a credit card or anything. These states are the states which are separable. And then you have to define in entanglement, in the source theory, we will see that a little bit, which operations, okay? See, if you don't have money, you will not have money, okay? So, and these operations will be ROCC, and we will talk. There are many resources theories in quantum information, because in some way it's beautiful, okay? I make a little bit of fun because a little bit turbo-capitalist, but there are also, for instance, symmetry, or you have non-locality, or you have discord, or you can construct for some resources, but it has to have some mathematical properties. It's not as trivial as that. But this is a resource of information. Entanglement is a resource. It allows you to do things that if you don't have entanglement, you cannot do it, and we will see. Okay. So, okay, now we go really to bipartite entanglement. And in this bipartite entanglement, this is a theorem, and it's a very important theorem. It's the following. It says the following. You have a state which is bipartite. I tell you, this state, it's bipartite, okay? And then there exists one basis. Bases, there are many, okay? So you have a basis, you make a unitary, you change the basis. But there exists one basis in which this state, which is bipartite, can be written in the following way, okay? There is one basis which is orthonormal. I will call it VI, which belongs to Alice. There is another basis which is orthonormal, which I call it UI. It belongs to Bob. And what I say is any state which lives in the Hilbert space of Alice tensorial Bob can be written in this way, okay? And this is not trivial at all. Okay, why? Because normally, right here, normally what you will do, so what I was doing before, let me show you. Before I was saying, you have a tensorial product, and what I was doing this thing over here, so sorry, but you will see the difference. Okay, so I was saying, if I have two bases, I can write it like that. Okay, and this is always, but listen, these coefficients of here depends on the two systems. EI belongs to Alice, and E2 belongs to Bob. So this you can always write. This is the tensorial product. But here I'm doing something different because there is only one index here. Okay? There is only one index. And this decomposition is special. This decomposition, it's called the Schmidt decomposition. And we will devote some time to that, and we will use it a lot. So there is a basis, there is a theorem that Schmidt did it, I think 150 years ago, something like that, in which it says, I can write, he was not talking about quantum information, obviously, okay. But what he did the following. He said, okay, I have a matrix, square matrix, I can always diagonalize it. But if I have a matrix which is, and I diagonalize it with a unitary, okay? I have a matrix A, and I can find a unitary of this matrix, which is U, D, U data, where U is unitary. This is diagonalization. But if the matrix is not square, you can also find the composition of this matrix, and it's called single value decomposition. Okay, so it's the equivalent to the diagonalization of a matrix, which is not necessarily square. Okay, and now I want to spend some time on that. These coefficients of here, they have to be all real and positive, and the state has to be normalized in my Hilbert space, so the sum of these coefficients squared are equal to 1. And these coefficients are called the Schmidt coefficients of the state. So, and the number of Schmidt coefficients has to be smaller or equal to the minimal of the two Hilbert space dimensions. What does it mean that? Well, it means that if I have one of the states, imagine I have a spin 1/2, and the other one is spin 1. What I'm saying is, it's impossible that spin 1/2 that has 2 degrees of freedom, it's entangled more than these 2 degrees of freedom. It cannot entangle 3 because it doesn't have it, okay? So, as maximum, it will be as maximum the minimal dimension of the two subspaces. Because the two subspaces, they don't have to be equal, okay? They can be completely different. 102. Well, I will have as maximal 2 Schmidt coefficients. So these Schmidt coefficients have a lot to do with entanglement. I'm telling you that this is in some way the entanglement. It tells me that there exists a unit basis which is orthonormal for Alice and orthonormal for Bob that happens that. Okay, so the first remark is the following, that the number of non-zero Schmidt coefficients is the Schmidt rank R, okay? And this basis, which is normally not the computational basis that we are using, sometimes maybe yes, but sometimes no, it's another basis, it's called the Schmidt basis of the state. The second remark is, if I look at that of here, I immediately realize that a bipartite state is in a product state if and only if there exists only one coefficient lambda. Because I say that the product state has to be of this form. Whoops. Has to be as a product. Has to be like that. Okay? So it can only have one coefficient of these ones. It's a product state. Okay? So if I am able to find this decomposition and I have a single coefficient, maybe the basis is super strange. Maybe I don't understand which is the basis because we are used to use this computational basis, no? The spin 1/2, 0 and 1. Maybe the basis is completely different. It's 0 plus 1, 0 minus 1, or whatever, or a phase in between, I don't care. But if there is only one coefficient, my state is a product state, it's not entangled. And conversely, if I have more than one coefficient, my state is entangled, okay? Like always, I define it is entangled if it's non-separable. And the third remark is that this Schmidt decomposition, I was saying it's nothing else than the singular value decomposition. So given a matrix which it's not necessarily square, okay, I can always decompose it like U, diagonal matrix P, where D is diagonal and U and B are unitary. Well, I put it the other way around, but it doesn't matter. Of course, U has the eigenvalues of Alice, and B has the eigenvalues. It's a unitary matrix, so therefore the columns of the matrix have to be the eigenvalues, the basis. And it has more things, okay? So, okay. So how do we find it? So I'm telling you, I give you a state, pure state, bipartite, okay? That doesn't work if it's not bipartite. Imagine that I give you a state very complex, which I have Alice has dimension 10 and Bob has dimension 6. So you know at least it can be 6 Schmidt ranks. And I ask you, is this state entangled or not? What do you have to do? you have to look for the Schmidt decomposition. And then you look at the Schmidt decomposition, you see that there is only one coefficient. This state is not entangled. So it's useless for many of the things that we want to do. This state is entangled, then you study how entangled it is. So how do you do that? Well, to do that, you have to look at what is the reduced state of a composite system. So I give you state, Alice and Bob, and I ask you, okay, I'm Alice, I see a part of the state, and I say, what is the thing that I'm seeing? I want to see which is this state, okay? So if my state is a product state, it's of this form, it's obvious that if I have a state which is spin up and spin down, I'm Alice, so I have my spin up, and you are Bob, you have your spin down, and I say, how is your state? It's obvious, no? My state is up and your is down. But if the state is entangled, and I ask you, how is your state? Well, this is not clear. What does it mean? Okay? It means that you have to measure, and then you will tell me how is your state. Okay, so imagine that I give you this state of here. Okay, so we prepare this state, okay, which is a state that I told you it's already entangled because I cannot write it as a product state. So this is 2 spin 1/2, 2 qubits, and it's in the state 0, 0, 1, 1. And I say, okay, I ask, for instance, Bob is going to measure in the standard basis 0 and 1, and now I want to see which is the probability that Bob gets a 0 or 1. Well, we use the postulates, postulate 3, we measure. What does it mean that I measure? It's only Bob who measures, that means Alice, do nothing. Okay, you stay without doing anything, identity. That means that you don't do anything, and Bob measures. And it measures on the basis 0, 0 and 1, 1, so one operator is 0, 0. And I calculate this, and this trivially gives you 1/2. And now, which is the post-measurement? I use postulate 3, and the post-measurement is that I get a new state. So I started by psi, and I get phi, which is 0 on Alice, 0 on Bob. I get this thing of here. Now, Bob says, okay, I'm going to measure now if it's a spin down, okay? And it measures, he measures, and says, Alice, you do nothing, and let me measure if it's down, and this will happen with probability 1/2, okay? And which will be state if Bob sees that it's down, down, because it's 1, okay? Bob does this measurement, the state of Alice and Bob will be 1 and 1. But that's fine. But what happens if Bob doesn't communicate to Alice what she has done? If she has measured 0 or 1. Okay, so this is the normal thing. So people, they don't communicate, Bob is making these measurements, you repeat that thousands of times, and the only thing that Alice can say is that on average, half of the times, her spin when she measures after that, it's up, and on average it's down, but she will never be able to predict if it will be up or down. Okay? So this is the measurement that she has, and this is exactly what you do when you trace out one of the systems. So you have Alice, what is Alice going to do? Alice, what Alice will see is that I trace Bob out, okay, and I calculate this thing. And tracing Bob down means that you make the trace only on the basis of Bob. And Bob does the same. Okay, what do I see? Well, what I see is whatever I see when I take Alice out of my system. Okay, and this is the trace. And when I do this thing of here, I calculate the trace, I obtain the following. So I take my state, I trace, and I have that Alice has this state with probability 1/2. She finds that the state is in 0, and with probability 1/2, she finds that the state is in 1, and Bob does the same. Okay? Well, this is the Schmidt decomposition in this case. Okay? So, let me put it like that. Let me put it like that. Okay. So, if I have this, I put an example which was very trivial to show it, but a priori it cannot be trivial at all. So if I give you a pure state, bipartite, any dimension, and I ask you, is this a state entangled or not? There is no way that you do, okay, let me calculate the Schmidt decomposition of this state. So first thing that I will do is calculate the reduced density matrices of Alice and Bob. And once I have done that, diagonalize them. Okay? Not only diagonalize them. And when you have done that, then you have done the Schmidt decomposition. And this is very easy to see here, because if I have my state like that, okay, and then I calculate the reduced density matrices, okay, so in the case of Alice, I put it wrong again, so this should be, no, this is the state of Alice, so I take out Bob, so I will have this state. And this is an orthogonal basis, so therefore in this basis, this matrix is diagonal, and this basis is diagonal. They don't have to have the same size, but they have the same coefficients. Okay? And then you have the Schmidt coefficients. Okay, so the Schmidt decomposition is the tool that gives us information about the entanglement of a pure state. Okay, some remarks that I already said before, but I will repeat it here. So first remark, I have my Schmidt decomposition, which a priori I don't know how it is. Okay, so when I will give you a state, it will not be written in the Schmidt decomposition, because why? Normally we work in the computational basis, which is much more simple. But then we know how to calculate this thing. We know that if the rank, okay, has to be as maximum this thing of here, so if we calculate and we have more elements, it's from the calculation. Okay. Now we can also define what it means to be maximally entangled state, because these Schmidt coefficients not only tell us if the state is entangled or not, but how much entangled we are. So therefore, I can define a maximally entangled state is the state that has maximal Schmidt rank, and all the coefficients of this Schmidt coefficients are all equal. So, can I have, for instance, a spin 1/2 and a spin 1 maximally entangled state? Well, yes, a priori, yes. Why? Because of this spin 1, I will have at most 2 coefficients that will be entangled with the spin 1/2. And then I forget if it was spin 1. If all the coefficients are equal, I have this big space which is maximally entangled with this one. I have a state in which I have a Schmidt coefficient which is very close to the identity, and the other one is very small, 0.9 and 0.1. It's entangled, yes, I have 2 Schmidt coefficients, it is entangled. It's very much entangled, no, because this is very close to have 1 and 0. So if I have only 1 and 0, I know that this is a product state. Okay, so the Schmidt coefficients are giving us some indication about what is entanglement and how much entanglement. It's a good measure of entanglement? No. Why? Well, because, I mean, to have a Schmidt coefficient is... no, it's not enough. So it tells us if it's a good, if it's maximally entangled. If I have 2 spin 1/2, I will be able to see it, but in general, okay, well, this is wrong. What they say, yes, it will give me a measure of entanglement, but I have to define what it is. No, it's not only that, okay, I have to define it, and it will be related. But if I say you have 3 Schmidt coefficients, and the values of these 3 Schmidt coefficients are 1 square root of 3, 1 square root of 3, 1 square root of 3. Well, this is maximally entangled. But if I give you 1 square root of 3, and then epsilon and 1 minus epsilon minus 1 square root of 3, what is that? I don't know. Okay? No idea. I don't know. One has to go a little bit further. And second, and third remark, which is very important, is that this Schmidt decomposition, unfortunately, only exists for bipartite systems. And why? Well, unfortunately, because it's a very useful tool, so we would like to have it for more systems. But yes?
Is there any equivalent of the Schmidt decomposition in infinite dimension?
In infinite dimensions? I don't know. No. Gottfried? As a Schmidt? I don't think so.
No, I mean...
Two Gaussian states to put...
like a Fox state.
I have two Gaussian state, I don't think it will be the same.
If I can apply this one to a coupled harmonic.
Because it's again, so you have to think that you are diagonalizing these matrices, so you have to have, also you can say I have matrices which are of infinite dimensions, but it sounds horrible, no? Infinite dimensions of the
Like, the
matrix.
simplest physical system is like two coupled harmonic oscillators.
Well, why I wanted to say why it's important that it's this bipartite, okay? Because mathematically, because I imagine that I have three parties, okay? How can I find the diagonalization of the matrices? Okay, so something like if I have two matrices, it's clear, no? So if I have a bipartite system, I can always find this diagonalization. A unitary, a diagonal matrix, and another unitary, which are different, okay? But if I have three parties already, that sounds horrible, no? Unitary, diagonal, no. I mean, this, you cannot break this symmetry. This is mathematical, the reason why there is not singular decomposition. And physically, also, well, one of the things that it's very difficult in entanglement is that it will be very difficult a priori that all the connotations of entanglement, they are linked to some coefficients. Entanglement is a very complex thing, no? So you can say, okay, imagine that I say, if the Schmidt coefficients are equal, 1 square root of 2, I know that this is the maximally entangled state. But if I have three parties, okay, what it will be to be maximally entangled in this respect with the Schmidt decomposition? Three parties, and not two parties which I have three coefficients. So 2 being 1/2, I have dimension 3, I can have 3 Schmidt coefficients. But if I have three parties, what does it mean? Well, Gottfried will tell us, okay? So it has to be that I have Alice, Bob, and Charlie. Alice and Bob are maximally entangled. Well, if Alice and Bob, they are maximally entangled, as we will show you, they cannot be entangled with anything else because entanglement is monogamous. Okay? It's like that. It doesn't like trios. Okay, so if you are entangled with Bob, forget maximally entangled with Bob, forget to be entangled with anything else. So all these things are very complicated and you cannot do it physically. Okay, so even to understand physically how it works is complex. Okay, so although in tripartite systems you can do things, they are, well, Alfred will tell us. So summarizing, I give you any state. You have a state. You calculate a state which is a pure state in the lab, assuming that in the lab you can have a pure state, which is something that we can discuss or not. I believe yes, but many people believe not. Imagine that you get that, and I ask you, is that entangled or not? So give me the mathematical form, and I tell you, okay, because I will be able to calculate the Schmidt decomposition, and if it has more than one coefficient, this state is entanglement for sure. And this is a very nice thing that we have. Okay, so I will say that that's it. We have done entanglement. So what we have done, we have put just the postulates, remember the postulates, and we have devoted ourselves to the fourth postulate, which is composite systems. Because entanglement is related to composite systems, and I have said, okay, so we can see if a state, a pure state, isolated, not interacting with anything, it's entangled or it's not entanglement, and we have some this Schmidt decomposition and so on. But I was telling you that entanglement is very useful for some of the protocols. Okay? Not all the protocols that they provide some quantum advantage require entanglement. It's also very interesting to say what is a protocol that provides quantum advantage. It's not so very clear, okay? So don't get confused for all these things that you can use constantly, everything is quantum advantage and quantum computer will solve all this. It's bullshit. It's not true, okay? So one has to be known what people talk about these things on the quantum advantage. But there are things that really, entanglement is beautiful because can do things, okay? And this is one of the most classical protocols, which is devoted to communication. Okay, so I want to communicate, and there is always like that. I am communicating, you are receiving, and I have a channel, which is this one, and I'm sending information to you. And it was a very important result from the 70s, from Colero Baum, in which it says that qubit, okay? We can never carry more classical information than n bits. And this was a little bit surprising, because if you have a qubit, superposition principle, I can put my qubit in 0 plus 1, okay? And this a priori looks like it has more information than 0 or 1, because you put this superposition. But Holebo, in a non-trivial way, showed that indeed this is impossible, okay? Because you can put your n qubits or 1 qubit in a superposition of 0 and 1, but when Bob measurement, because there is no way to get information without measuring, this advantage of the superposition is lost. Okay? So there is no way that you can communicate more using a channel, using a single qubit or n qubits, or using classical bits. It's the same, very deceiving. A few years later, Bennett and Weissner, they showed something which is very nice. They say, no, okay, if I consider as a resource now that I can use the channel only once, okay, I can send something to the channel, I can only use it once, I can communicate more. If Bob and Alice, they already have an entangled state between them beforehand. So on all these things, it's like a game. You have a protocol and you have to put the rules. Now the rules is that Alice and Bob, before they have met themselves and they have decided to share a maximal entangled state. Okay? And now Alice, with this maximal entangled state, she wants to send, okay? And she will send. So a maximal entangled state, it's 2 qubits, okay? In a maximal entangled state, 0, 0 plus 1, 1. And with that, Alice, which is here, wants to send, okay, 2 bits. Okay, so 2 bits, she wants to send either 0, 0, 0, 1, 1, 0, 1, 1. But she only wants to send 1 qubit to the channel. Okay, she wants to use the channel only once. So Holebo tells us that this a priori is not possible, but Bennett and Weissner told us, yes, this is possible, and the trick is the following, okay? Use an entangled state, okay? So what do they have to do is use this state, 0, 0 plus 1, 1. So this state we have before me, and we have decided that I have one of these qubits and you have another, or it can be a third party, Charlie, which sends us, to each of us, to Alice and Bob, one of these entangled states. And now, how is the protocol? Well, now that works, okay? And this is incredible, because Alice says, okay, I want to send my 0, 0, okay? And what I'm going to do is, I will do nothing. Absolutely nothing, okay? Good. Now, I want to do 0, 1. I want to send to Bob 0, 1. So if I do nothing, of course, the state after that is the same state, because I have done nothing. So I started by 0, 0 plus 1, 1. So I do 0, 0 plus 1, 1. Okay, I want to send 0, 1. Okay, what Alice has to do? Alice has to do an X rotation. Okay, apply sigma X to her qubit, okay? And then send her qubit to Bob, one single use of the channel. If I want to send the 1, 0, okay? So what I have to do is a NOT gate plus Z. And the state that Bob will get is 0, 1 plus 1, 0. And finally, I want to do, Alice says, I want to send 1, 1. Okay, what I have to do? I'm Alice, okay, I have to do an X rotation and Z rotation, or whatever is the same, because these are Pauli matrices, E times Y rotation. And my state, after I have done that, Bob has done nothing, okay? Bob is in his place, just waiting, okay? She gets, the state is 0, 1 minus 1, 0. Okay, so now I'm Alice, and I'm able to do these things, and when I have done that, I send that to Bob. And Bob ends up, okay, with 4 states, which are, depending on what I have done, 0, 0 plus 1, 1, 0, 0 minus 1, 1, 0, 1 plus 1, 0, 0, 1 minus 1, 0. These 4 states are orthogonal. Okay? They are orthogonal. Therefore, quantum mechanics tell us that if I have orthogonal states, I can distinguish them. How do I have to do to distinguish? We will see, but I can distinguish them. So this is a basis. Okay, so just by sending one use of the channel, I can send 2 bits of information, of classical information. Okay? And this is only because there is quantum entanglement. It's very nice. So I agree with me that it's a simple task that you cannot do it in any other way. Okay, so this is the first example. Of course, you have all here about teleportation. It's the same at the end. Okay, you can teleport using that. But this is even simple. Okay, so with one use of the channel, so I send a quantum bit. I'm Alice to Bob. I'm just manipulating my state. Before I'm able to send 2 bits of information. This is not against Holebo bound at all because I have an extra resource, entanglement, my money, bam. Okay, then I can do it. So, for instance, imagine that I want to do that. Okay, so imagine that I want to do this. I want to send 1, 1. Okay, I have my state. I want to send 1, 1. I apply sigma z, sigma x, or y times sigma a on the qubit of Alice. I send these things to Bob, and now Bob has to perform this C0 gate, okay? Then he has to perform a Hadamard gate, it's like that, this is the protocol, and then Bob measures on his qubits, now he has 2 qubits, his own qubit and the one that Alice has sent, and he obtains with probability 100 the 2 bits that Alice has decided to send it. Okay? So it's a very nice, so we only have to use this is 0, 0, for instance, it's even simple. Okay? So if we do this 0, 0, we have to use just the postulates and the post-processing, and this is 0, 0. It's a very simple protocol. Good. How are we doing? Fine? Yes? Very tired? Okay. You are ready for the second part? Yes. Okay, so now we are going to the second part. Okay, so this was first part, which is pure states. And now we are going to mixed states. Okay, why mixed states? Why we are not staying with pure states? Why? Because pure states, they exist, but experimentalists, they will say no. So most of the cases, oh, let's put it like that. Okay, there are many things that you can say. There is impossible to have a state completely isolated. So the interaction, it's not completely true, this thing, that it's not possible to have a state completely isolated, but it's quite difficult. Okay, so as soon as your state is not isolated and has interact with anything, you will have a mixed state. That's clear. Some people say it like that, some people say that experimentalists, I don't like to do that, they are experimentalists here, they always make errors, and they are not able to do the things properly and present pure states, and therefore you end up having mixed states. I have a big respect for the experimentalists, and I don't think this is the reason, right? So even if you don't try to do it. So in most of the cases, we are not going to work with pure states, but rather with mixed states. And what is a mixed state? Well, a mixed state, it's just definition here, an ensemble of pure states. It's a situation in which I have a physical system, which can be in many different states with some probability. So I have my typical example, spin 1/2, and I say, okay, I have prepared it with probability. For instance, 1/2, I have prepared that it's up in the z direction, I put the Stern-Gerlach and so on, and because sometimes there is some things and so on, with some probability, is it 1/2 it's down, okay? Which is my state? Okay, this is not 0 plus 1, no, this is a superposition, okay? These are very different things. When I do a superposition, that my state is in a superposition of 0 plus 1, and I write that as a vector, I write it in my basis, And the coefficients that it goes in front of the superpositions, they don't have to be probabilities. It can be just complex numbers. Okay? It's a superposition.
Is this probability a quantum probability or classical probability?
These are, what do you mean? Probabilities.
It's like in the superposition, there is square root of 2.
But in the superposition, the numbers can be complex. Okay, and then you say it has to be a unit vector. So the sum of all the conditions, modulus squared, it's equal to 1.
Yeah.
Okay, but the superposition, you write psi, it's the sum of ci times e. This c, which doesn't have to be a real number, it's a superposition. Okay? While when I'm writing that, this is a probability, and a probability is a real number. Okay, can never be a complex number because that would be very complicated. Which probability you get, you are sitting? And square root of 1. No, it doesn't exist. Okay, so you are 1 or 0. So probabilities are real numbers always. Okay, and it has to be very clear the difference between a superposition and a mixed state. It's completely different. So that you see it clearly. Right. For instance, okay, this is a superposition, coefficient square root of 1/2, and that's the. Okay. But this here, is a superposition. Okay, number 3, and this is a complex number. Cannot be a probability. Okay, so this is very different. So I go to mixed states, bam, 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 here, okay? And I say that a mixed state, it's a state that describes that my physical system can be in different quantum states with some probability pi, okay? So, of course, the sum of the pi's has to be equal to 1 because this guy, we will see the trace will have to be 1, that's sum squared. And these have the different states, and each of these pure states, it's normalized. Okay, some remarks. This index, it can be continuous or it can be discrete. Here, there is no difference. Okay, I can have that my index, it's an harmonic oscillator, okay, and my state, it's in a superposition of all the states of the harmonic oscillator. But the harmonic oscillator, by definition, if it's not gathered, has infinite states, alright? It can be in a superposition of all possible states of my harmonic oscillator. It can be continuous. Normally, we will write it like that, okay? So if I have, I can write it like that or like that. It's the same. It means with some probability, the state is inside. And it's not a superposition, okay? Listen how I write it. This is a matrix, okay? It's an operator, and this is a vector. So mathematically, they are completely different animals, okay? One shouldn't discuss it. And now if we want to see how are the postulates, because we will have to use it, well, the postulates, we can always think it in this way, since this is an ensemble. And now, if my system, each of these states is isolated, okay, still the evolution will be unitary. And what will be my final state? Well, my final state will be that with probability pi, my state will have evolved under this unitary. My state psi I will be under this unitary. And measurements, how I will going to do the postulate of measurements? Well, the postulate of measurements the same way, okay? I will have, remember how it was this postulate, let me go on to the beginning. And now I just repeat the postulate. Sorry. What? Okay, so how was this postulate? I was saying that if I have a single state, psi, okay, then the probability, when I do a measurement, I have my measurement, okay, the probability that I get the outcome m, okay, is this expression of here, okay, which is trivial to see it because you say, okay, what happens? My state has changed to this thing of here, and now I have to normalize it. Okay, so I calculate this. And now when I go to the density, now I do the same. Okay, I can consider it, sorry, like that. Okay, I say, well, with probability, so for each state psi I of my ensemble, which was given with probability pi, now I will have the probability that if the state was in psi, it gives me as an outcome k, small k, okay? Which is this probability? Well, now it's the same probability like I was using for a pure state. My state is in I, psi I, and I apply nk and gives me this probability. And which is the post-measurement? The post-measurement is this one. Okay, so now I have a new ensemble, and this ensemble is pi, q, ki, okay, or probability psi I of k, psi I of k. It's a little bit more complex, but like that. So if now I want to write the postulates, and this is how you have to learn the postulates, the other thing it was just warming up first day, it's like that, okay? So the best thing is to forget about pure states and only talk about that. So this is how I understand it. Okay, maybe, yeah, finish, and we will finish here. So this is how I understand it. What is quantum physics? Quantum physics is a mathematical formalism to describe the world. Okay? It's a mathematical formalism. Okay? And there is some rules, very simple rules, that tells us how to work in this mathematical formalism. The first rule of this mathematical formalism is that I have to describe a physical system, and I have to describe it in such a way that whatever measurement I do in this physical system, I obtain, or it's coherent with what I obtain. This is the first, okay? So, nothing else, okay? This is the first. The second thing, it tells me, it's a mathematical formalism that tells me whatever transformation I do on my system, and after I measure, it has to be coherent with the mathematical formalism. So if I obtain something in the lab, okay, which is not what I have prepared, and it's wrong, the formalism is wrong. So maybe somebody at some moment will show that quantum mechanics is wrong. That would be fantastic because you will have a lot of work, okay? But it's possible, no? That suddenly you can get the measure, and imagine how many years doing Bell measurements in order to see if it's true or not. If you get a result which you cannot explain with the theory is wrong. Okay, but quantum mechanics looks for the moment it's right. So the way to do that is the following. Postulate 1. Associate to any physical system, there is a density matrix. Is an operator, so it's not an element of H. Is an element of the bounded operators of H. It's a matrix, okay? Which has to be defined positive. Okay, so eigenvalues in the finite systems, that means all the eigenvalues of the matrix has to be positive or equal to 0. It's semi-definite positive, sorry. And the trace has to be equal to 1. Look, I didn't put that it has to be Hermitian, because for finite systems, if the matrix is definite positive, it's Hermitian, for sure. Okay? It's not an extra, it got included. If it's not finite, then it doesn't have to be. Okay? If the system is in the state psi I with probability pi, then the total density matrix is given by that. Pi probability is rho I. First postulate. We don't need anything else. Pure state is a reduction of that. Okay, that's it. Second postulate. Forget about unitaries. It's a reduction. Second postulate. This is how we have to see it. The evolution of a quantum system, the evolution, whatever happens to a quantum system, it's described by a completely positive trace observing, it's not increasing, map. And this is a map, okay, which goes from operators to operators. It cannot be a matrix. We say that a matrix transforms a vector to a vector. It's a super operator because now I'm looking how to transform a matrix. And I don't transform and multiplying by a matrix. It's a super operator. We will see. It's the same, but this is what we call the charge of the Hilbert spaces. We always go a little bit up. How super operators change with super operators, okay? how the Hilbert space with super. So this is the charge of the Hilbert space, and we will do it like that. Yes.
Why here you define as open system?
Sorry, say again.
Why are you defined as an open system?
No, it's not an open system. No, it's not.
Closed system.
It's not an open system. That the fact that I write it like an operator, I cannot write it a unitary here. So if this thing is a unitary, I will find a map which is unitary.
Still closed system.
But here, I say, oops, okay? What do I have? Is that if I have a density matrix, and it evolves, it has to have a density, it has to be a density matrix. I have this and false, but this can be broken, but it's a physical system, it will be a physical system. Okay? And I have to demand that it's, let's say, that it preserves the trace, that it's a physical state. And it's not true. This involves everything, open and closed systems. That's the reason that postulates have to be learned like that. Okay? And the three, I don't care, measurements, we have seen it. And the fourth, which is the one that we are interested in, and I will finish here. Okay? The state of a composite quantum system is described by a density operator, again, where this density operator lives in the tensorial product of the Hilbert spaces. But it's a matrix, always a matrix, okay? If the state of each, now here we go, with our definite definition, if the state of each constituent is given by rho I, then the state of the composite system, it's like that. And it's separable, it's not untangible. Okay, if I'm able to write it like that, that's fine. Okay, and I will finish here for today. Thank you very much.
We have time for questions. Yes.
Do local measurements always destroy that variable?
Sorry, I will be here. You can ask me always. Okay, these days. I mean, about it now. If you want to ask any these days, or I'm here to answer whatever I know. Yes.
Thanks. So my question was, do local measurements always destroy entanglement? Because in the example you showed us, okay.
No. For instance, let me give you a very stupid example.
Yeah.
I have a local measurement which is do nothing. Okay? It's identity. Do
Yes.
nothing. So it's local and it will not destroy.
Okay.
But you have to be, this is a triviality, okay? But,
Right.
you know too much. I mean, I know you know too much.
So in this more general formulation of the postulates, do I need the third postulate, the
Measurements.
Can I describe the measurement as a...
No. You need the measurement. I didn't put it here because it's not so relevant, but you need the measurement postulate. It's not almost.
It's weird, man.
Without measuring, there is not one.
It's
So you have to have the measurement postulate because this is what it tells you. Whatever you get has to be compatible. The only thing that I want to say is a density matrix is a mathematical object that has to fulfill that whatever measurement I know how to do, or I will think that I will be able to do. Maybe I cannot do it today, but in 10 years you can do it. Has to give you a result which is compatible with the description of the system. This is a density matrix from a physical point of view. From a mathematical point of view, we have seen it. It's a density matrix and so on and so forth. There is one, positive.
Sorry, just a comment. Because in the previous postulates, we said that the evolution must be unitary, but the measurement will not be unitary. So it feels like a measurement is something metaphysical. It cannot be described by a physical evolution. Whereas here...
Okay, we don't say that it's metaphysical. As Christian that is going to talk now, and he's an experimentalist and he measures things. No, you measure. And it's metaphysical. Okay, no, but these are two different things. One thing is the evolution, okay? Evolution, and the other thing is the measurement. So, evolution, you don't ask that the sum of m daga m is equal to 1. You don't ask that. you can have an evolution which is not unitary measurement. It's a set of operators that they fulfill that. Because the probability that you get an outcome, if you look, has to be 1. So it's
So I have seen before the postulate 2 written as the action of the unitary evolution given by multiplying a unitary matrix by left and it's adjoined by the right. I would like to know if this is equivalent to the postulate 2 you have written, if we can always recover such a unitary matrix.
Yes, you can do it. We don't have anything to write here, because that will be easier. Yes, you are right. So what I'm saying is that when we do things at the level of pure state, we think this is, maybe this will be. It's very silly, no? But imagine that I have my density matrix which corresponds to a pure state. It's like that, do you see? This is a density matrix, is an operator, but it corresponds to a pure state. And it's isolated. So how is the unitary evolution of that? Well, or in any case, so U, rho, U gamma. This is rho of time for an isolated system. So as you say, U, rho, U gamma. When I say, be careful, because this is the evolution, okay? As you were saying. On one side, you have the unitary and the unitary. It's a unitary evolution. What you have to be careful, and I want to say it's because, of course, I cannot say that rho of t is an operator, call it 8 times rho. It's not like that, because I have to operate in the 2 sides. I have a u on this side and a u dagger on this side. So I'm putting 2 matrices, and here I'm putting a matrices, no. Okay? So this is why I generally write that I have the evolution, okay? It's a map, whatever a map is, we will see it, okay? That applies on rho. And this map has to be positive. That means that if this guy is positive, this is a physical system, positive, has to have trace equal 1, and has to be what else? Has to have a density matrix, and it's an operator. That's it. This is the typical evolution. Okay, and this includes this thing from here. Yes?
Yes, but given any operator, not operator, any function that satisfies the postulates 2, can we recover the
Any function that satisfies postulate 2, postulates 2 tells me that if in the way that I would like that you remember, postulate 2 tells me I have a physical system described by a density matrix. How this physical system will transform under whatever it happens, okay? Just putting this here. I have an atom here, okay? How it will transform being in this room and so on with an operator like that. After a time, it will be like that. How is this operator? I don't know. I mean, it depends on the case. It's exactly the same postulate. It's identical. Think of it like that, okay? Psi transforms like u times psi. Okay, rho, it's the sum over I, P, I subset. If it's unitary, each of them will transform with the unitary. But if it's not unitary, open quantum system, not unitary, it will transform also like that. So this is the best way to learn it. Okay. Density matrix transforms according to a map. That's it. And the details of the map is secondary. We will see it.
Okay, thank you.
I think. I was going to say.
Sorry, I just have one remark because Anna asked before. So any student is interested in helping us in writing some LaTeX notes about reflections about entanglement, yeah, please contact either me or Anna.
you should be more enthusiastic. Your name will appear in the lectures that we will put in the archives with us. Okay? If not, I don't see that they are very happy about it.
Okay, so let's thank Anna, and she will be here so you can ask questions.